PreCalc. So this is your lesson on 10.3, which is an extension of our geometric sequences. We're going to take these out and do some geometric series, just like we did at the arithmetic sequences and series. So I'm caught in my cords, but we are on a worksheet. I want you to follow along with your notes, and you need a graphing calculator handy as we go along as well. So I need all of my pieces of technology to behave all at the same time, and then we're in business. It's not looking good. All right. Everything's flickering. It's always a good sign. All right, so a geometric sequence, remember, were the formulas where you were multiplying by a common ratio each time. And then I'm sure it's on your notes somewhere here, but there we go. The geometric sequence notation is what we saw last week. R representing the common ratio, and then to the power of n minus 1. And all of that is being multiplied by an initial term of a sub 1. That's old news. All right, so the next thing we're going to talk about is what if we have geometric means. So we talked about arithmetic means, which followed an arithmetic pattern, which meant we were adding a common difference each time. Well, a geometric mean is similar, except you're going to be multiplying that common ratio in. So the setup is similar in a sense where we need to look at how many hops or jumps or whatever you want to call them we did. So to go from 6 to 162, there's two geometric means in between it. So you multiplied by something not once, not twice, but 3 times did you multiply by that common ratio. So the formula that we're going to set up, or the equation we're going to set up, is that you start with 6, and then you multiplied by this, whatever this common ratio is, and you did it 6, no, not 6 times. What did we do? 1, 2, 3? 3 times. And it got you to an answer of 162. And then this is an algebra statement that I need to solve. So I'm going to divide both sides by 6. And that leaves us with r to the third power equals, I think we've all agreed I should stop doing mental math, so I'm going to cheat, look at my answer key, 27. And then, of course, to cube root each side of this equation would give you the solution of r equals 3. So your common ratio is 3, which means we multiply by 3 each time, and I like to just kind of fill in the geometric mean so that way I can tell that I didn't screw it up. So if I multiply by 3 here, I get an 18. And I should be able to do that in my head. I'm done doing things in my head, guys. I don't know. Am I the only one who feels that way? All right, so then it's a 54. And then just to double check, if I multiply that by 3, I totally get 162. So I did something right. Go me. So very similar to arithmetic means, except now we have that hopping of multiply factors. The common ratio is being multiplied in. All right, so another example of this. We just did that question. Ignore me. This one, the geometric sequence has 3 geometric means in between them. So that means you start with 7, and then you've got 3 blanks, but we got to be careful what that really means for geometric means. You multiplied not just once, not just twice, not just 3 times, 4 times. All right, so you started with a 7, and then you multiplied this common ratio 4 times, and it gave you an answer of 567. Yeah, I'm not going to do that one in my head, guys. I don't even have this on my answer. All right, so divide both sides by 7, and then we grab our handy calculator. And I got to be able to type. That's my next issue. That's 81. Oh, okay. So let's talk about this for a moment. 4th power, right? It's an even power, so when I take the 4th root, technically my answers are both positive and negative. So the 4th root of 81 is 3. So technically right now my answers are both positive and negative 3. So now I have to think about, like, okay, does that work for this problem? Like 3 is fine because everything would be positive as you multiply by 3, right? So you multiply by 3 here and you get 21. Trying to see if I secretly have this one filled out. I don't know. And then, what am I multiplying by 3? All right, so that's 63. And then 63 times 3 is 189. And then just to double check things, 189 times 3 is totally 567. Now, if I used negative 3 as my common ratio, that would have made this a negative 21. This would have then become a positive 63. This would have been a negative 189. And this would have been a positive 576. So technically speaking, your common ratio on this question Could have been both positive and -3. That was a bit of a trick question, I think, guys. I don't think I'm going to trick you like that on a test, so don't panic, but that is a good SAT question. All right, write a geometric sequence that has one geometric mean. All right, so it's the same idea, guys. You got -5, there's one mean in the middle. It's going to get you to -31.25. So you would have to multiply not once, but twice to get there. So you'd start off with -5 times r squared, because of the 2 hops, would be -31.25 as an answer. And then dividing by -5 and square rooting. I got 2.5. Now again, you got to think about, okay, square rooting, so is the answer both positive and -2.5? Well, if it's positive 2.5, I multiply by positive 2.5, and I get a negative whatever this number is. I really should be able to do this, huh? So that would be a -12.5. But if I use a -2.5 as my multiplier, okay, that would be positive 12.5, and then multiply by another negative, it would be -31.5. So again, this is a case where either one of those is going to work out. All right, I'm just kind of previewing my worksheet here to make sure I didn't misspeak on that question. I think we're good. All right. If I have an epiphany later, I'll come back to that question, okay? Hi, daughter. What's up? You done? No, I'm not done. All right. So just like with the arithmetic formulas, we saw that we could sum all the terms together for the arithmetic sequence. We can also sum all the terms of a geometric sequence together. There's 2 formulas. Mrs. Hoffbauer put a little X next to that bottom one. We don't like that one. We don't use it very often. And they're both kind of annoying to type. So there's a big note here about needing more parentheses. What she is referring to, and I suggest you do this on your notes somewhere, is that you sneak in some extra parentheses around your numerator. Ooh, that didn't work. And around your denominator. But what everybody forgets is that this overarching parenthesis around it has to be there, and then your a sub 1 term out in front. Wow, that is not clear. Okay, so that is for a finite geometric series where you have a beginning and ending term. There's also something called an infinite geometric series, and that's kind of hard to understand when you're first being introduced to this topic. You're like, how can something add up infinitely and then add up to like a value? Like, how can I say the answer is 7 when it like never ends? And we're going to see in a moment that the issue is that your series converges down to a value, almost like an asymptotic behavior. And that it's kind of a cool concept that you use a lot in calculus. So we will talk a little bit about that. Here's a good kind of notation of how you need to use your parentheses. You will notice on Mrs. Hoffbauer's example here, she doesn't have the extra parentheses with the a sub 1. That was my misspeak. You definitely don't need those. This is the kind of parentheses we need to be using. So notice how r is in its own set of parentheses. Let me go back and fix my... I don't want to mess anybody up later. Scrap that. All right, let's see this in action, guys, okay? I already forgot the formula. I'm going to show you some neat stuff on your calculator in a moment, too, because if you're like me and you're thinking, I don't really enjoy this formula as much as I was hoping, and I want to use my calculator, I'm going to show you that some of the sequence stuff again. All right, so we're going to sum the first 12 terms together. The formula for this being finite is... All right, so it starts with the first term, which clearly is a 6. And then in the numerator, I always get this guy wrong. It's 1 minus, and this is where it gets kind of crazy because you're like, wait, what's r? Well, remember in our geometric sequence problems, if you had to find r, you just had to take the second term and divide it by the first term. So for us, if we took 7.5 and divided by 6, again, no mental math happening here, that is 1.25. Now notice I wrote that as a decimal and not a fraction. for the sake of habit, I'm going to put parentheses around this. Oh man, I got a little ambitious with my parentheses. Let me erase that. Because then it needs to be, that r only needs to be raised to the nth power. And they want 12, right? 12 terms. So this is raised to the 12th power. Then you close your numerator. These are a pain in the tushy to type, can you tell? And then down in the denominator where you have another set of parentheses, it's 1 minus the r. Now technically here you do not need parentheses around the r because there's no exponent on it. I suggest everybody pause the video right now and try typing this. And let's see what we can do while you watch me type. Notice I'm not even typing on my correct calculator because that's how much of a day I've had, guys. 6 minus 6, no, not 6, 12th power divided by 1 minus 1.25. Again, if you used a fraction r, that's fine. And you're going to notice this comes out real funky. Alright, and if you try to hit math enter, you're going to see that it's still real funky. So I'm just going to write out this answer. 2, 4, 5, 9, 6, 5, 5. And that's not even a truncated or rounded answer, I don't think. If you needed an exact answer, which often in math team and SAT questions, they want something a little prettier looking than that, you would have to calculate the numerator and denominator separately and do some like 5th grade math style. I don't got time for that today, guys. We're not going to bother. Now, side note. Remember that sum of the sequence stuff that we did? Well, you can do it on geometric too. So just like on our last lesson, when we learned how to pull up sum of the sequence, you would start by writing your formula. Now the formula they're referring to is this geometric sequence that this is following. So the geometric sequence started with a 6, and then it multiplied by a common ratio, which we decided was 1.25, to the x minus 1 power. Remember, in this type of function mode on your calculator, it's going to use x. Now, I believe, correct me if I'm wrong, kiddos out there in the world, I think your calculator ends up using this kind of notation for the exponent when it pastes it into the formula. I don't know why I switched colors on myself. Let me go fix this. So this is kind of a pain to type, regardless of your method of choice here. All right, so there's our explicit formula. We're using x as a variable, and they want the first 12 terms. So we would start at term 1, and we'd end at term 12. So summing the sequence that way works too. Let me pull up my calculator, see if I can show you how that types in for you. Again, some of you got crafty and you just started using your old answers and just editing them. But all right, so sum is found in lists. So second stat, math number 5. Stay in that command, go back to that menu, go to ops number 5. All right, clear that out. I already forgot what it was. It was 6, right? All right, 6. And then 1.25 was our r, which we did have to find. That's kind of annoying. And then up in the exponent, we got x minus 1. Ooh, it doesn't do it good. All right, I need to put parentheses here. So it doesn't use that cool notation that we're so used to on our calculators. You do have to put parentheses around the x minus 1. All right, 1 to 12 was it? All right, fingers crossed. Here comes a really ugly answer. Yeah, there you be. All right, so it's up to you guys. The other formula, this guy, is really horrible to type, but turns out it's horrible to type in some of the sequence as well. So I'm going to leave it up to you guys how you want to practice this, and I'll try to like flip between the two methods on the rest of our examples here. Mrs. Hoffar wrote me a note that she skipped number 5. I don't care. I'm all right with that. What is number 5? Okay. She just renumbered, I think. All right, so the sum of the first 7 terms. So again, you could figure out the 7 terms, but that seems like too much work. So first you have to notate that, or make a note that it is geometric. looks like we are multiplying by, that'd be a 4. So the common ratio is 4. And if you weren't sure about that, you could find the common ratio by taking the second term and dividing by the first term. That's always an easy way to come up with the common ratio. If you can't see it, like on that previous example, it was awful. So we want to find the first 7 terms. If you want to use that newer formula, you sure can. All right. Sum of the first 7 terms. It starts off with the first term, which is -1. And then, this is where it gets gross. All right, parenthesis for the numerator, 1 minus. Now this is kind of confusing because kids are like, do I need the parentheses? Do I not need the parentheses? You really don't need them around this r. However, I think it's always a good idea to put parentheses around r as a force of habit for you. 7 terms, right? So up to the 7th power, then close your numerator. And then in your denominator, you got 1 minus r, which you don't need the parentheses here. So again, this set of parentheses right here is technically optional on this particular example because your base, your r, was not a fraction and it wasn't negative. We know how exponents are affected differently to different problems, but force of habit, use parentheses. You know I don't like this method, so I would have never done that. So instead, I would have done sum of the sequence. And I'm going to write it out using the old calculator notation. Remember, this is the stuff that your calculator will paste into. But first, I have to write it. So my explicit formula was -1 times r. And then remember, we just realized it does that weird caret thing. So to the x minus 1 power. And then comma variable x, comma, start at 1, end at 7. And then when I plop that in the calculator, I get negative 5,461. So pause the video, try typing. I would suggest typing both of them. You really have to start making a decision which way you would like to practice this, because if you're like me these days, you want to get this done as efficiently as possible. So your choice. Alright, so here we have a sequence with a first term of -2. They go ahead and give me the r, and they tell me the 9th term, and they want the series, which means they want me to add it up. So again, it's up to you. Which way do you want to do it? So using this new formula, we're doing 9 terms. I sure could. I could say my first term is -2, and then I'm going to multiply it by 1 minus r, which is 5. Again, the parentheses are not required around this base of 5, but I suggest it. I already forgot what we're doing. To the 9th, okay. To the 9th power, close your numerator, and then that's being divided by 1 minus 5. Again, you don't need parentheses around that 5 in this case, or in any case, because you're not raising it to any power. Do watch your parentheses around the numerator and denominator, and just be really careful about this part here. If you didn't like that method, you could have done sum of the sequence, which I'll be honest is the way I would have done this question. So I would have summed the sequence, hey log, of -2. I'm not using my colors, let me back up a minute. -2 times r. Remember, your calculator does this weird thing. X minus 1 power. And now I wrote too big. X, comma, 1, comma 9. Woo, pretend you can read that. Either way, kind of hoping I did this question. I didn't do this question. I think Hofbauer made up this question. It's fine. It's good because it's like your homework question. Alright. We're going to sum that sequence. Hey, Log, what do you think about all this? Seems easy?
No.
No? It's not easy. I already forgot the question, darn it. -2. Ah, come back. 5. I think I might be making up this problem. X minus 1 power. X is always that, and I think we went to the 9th, right? Yeah, cool. All right, paste. Hope that was, oh, God. I forgot to do that. Okay, it's okay, easy fix. I forgot to sum it. So, where are we at? Sum. We need to sum this. Sum, and then I'm going to cheat, and I'm just going to say, okay. No, not that guy. This is a sign that your math teacher should be quitting for the day. But no, guys, I'm going to persevere. See if it'll do it if I do answer like that. Yeah, that seems right. All right. Guys, remember this number for me. 976562. 976 and I think it was negative. Man, I hope that was right. You know what? Just for funsies, let me type it in the other function, the other formula, excuse me, and see if I can get that one right. I'm going to type it in my calculator, though, just to make sure I'm not losing it. Negative 976562. All right, nailed it. Whew, guys, this is just a hoot, isn't it? Oh, look, our friend the sigma notation. So remember, this is a series notation. It indicates that you're supposed to sum all of the terms together. And the reason we're bringing it back is because this guy clearly is a geometric formula. Because it's got that, you know, r to the n minus 1 power. So this is your explicit formula, and this is a good candidate for sum of the sequence. So this time I'm going to remember to sum the sequence. And I'm going to just type that guy in. Now, again, I got to be careful with my calculator. It's 5 times 1.06. And our calculator will use x for the variable instead of n. And then it says 1 to the 11th term. So you're going to start at 1, and you're going to end at the 11th term. Yay, technology! All right, so when I get this typed in, I know I'm going a little over on time, so I'm going to just steal my answer. Ew, 74.8582. And we knew it wasn't going to be a beautiful answer, but that's what technology's for, right? All right, moving along. Okay, some notation here. It says find the sum of the first 16 terms in a geometric series, where your first term is 1, and then it gives you what we know is a recursive formula. All right, so, hi baby. We can use the formula that we've been using, or we can use the sum of the sequence, but the key is that you can kind of pull apart what this recursive formula is saying. It's saying -2 times your previous term. So that tells me the common ratio is -2. That's what that big clue was, okay? So if I want the first 16 terms, again, you can use that newer formula, or you can sum the sequence, but the idea is you got to be able to type it. So this newer formula will have us take the first term, which is a 1. Well, that's boring. And then 1 minus, now here's a case where you most definitely need parentheses around the -2. And then to the 16th power. You're going to close your numerator. And then you're going to divide by 1 minus, and again, you don't need parentheses here, but I know a lot of kids like to use parentheses when there's double negatives like this. But make sure that you have parentheses around that denominator. However, if you're a big fan of sum of the sequence like I am, you probably did it this way. You said sum of the sequence. Okay, my formula started off with, this is a case where like you might type more than you really need to, but whatever, it's a force of habit, right? So 1 times -2 to the x minus 1 power for the n minus 1 part, comma x, comma, what is it, 16? So 1 to 16. And that is another way to get the answer. And I know you've been dying to find out what the answer is. Me too. It's -21845. Isn't that lovely? All right. So that is a good example of recursion coming back now in a geometric series. So that was super fun. Real quick, The topic of divergent and convergent. This video is running a little long, so I'm going to skip it, but the idea is if your common ratio is smaller than 1, so like a number like 2/3, right? So it's going to be, you know, like decaying down to nothing eventually. It's going to have like this asymptotic behavior. And that allows you to have what's called a convergent geometric infinite series. So even though it goes forever, infinite, you can still come up with a sum, which is kind of cool. It's the idea of a limit that we're going to get into soon. If it's divergent, that means it goes up, 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 up forever. So your ratio is bigger than 1. So if you multiplied by a 2 every time, you know, that would just get bigger and bigger and bigger without bound. And you wouldn't be able to sum your sequence anymore because it would just go up to infinity forever. And therefore you wouldn't be able to find it. You'd say like the sum is infinity, which is silly on its own. So we're not going to get into that topic. Here's a neat question here. I'm not sure what's on your homework, so I want to make sure that we do this one. An employee has a salary plan where your annual salary increase is 4.5%. Here's the initial value. So this is like your A sub 1. And then of course this is your R, kind of. Remember, even back in Algebra 2, your R is 1 plus that little decimal. Okay, because you got to grow. If you just put 0.045, you'd be like taking off a bunch of money from their salary, and that wouldn't be cool. So this is where kids kind of get into trouble because they're like, okay, well, in Algebra 2, the formula was to the t power, and the one we're doing today for geometric has like, you know, x minus 1 or t minus 1 in the exponent. So you have to think about what that really represents. What was his pay for his first year of work? Well, we already know. Oh, ignore. Oh, this has been a bad video. I apologize, guys. He earned this on his 10th year of work. Scrap that idea, Bruzo. All right. So, here's what we're going to do. We're going to take this problem. I'm going to use this workspace down here. And I'm going to say the answer to the 10th is $50,081.41. There we go. I don't know his initial work pay, like his first year, but his common, his raise increase, remember, is 4.5%, so that's 1.045. And then that was his 10th year of work, remember? So up here, this would be like 10 minus 1. Because, and this is kind of hard to understand, but he didn't get 10 raises, right? He started off with pay, and then he got 9 raises. So that's why that exponent's really a 9. That is what confuses kids the most, right? All right, we're going to solve this by taking whatever this atrocious number is, and we're going to divide it over. And I don't really have any work here, so I'm just going to tell you when I did that. His first year of pay turns out to be $33,700. Okay, so that was part A. And then for part B, to the nearest dollar, how much did he earn in his first 10 years of work? Well, this is a case where you are welcome to do some of the sequence. You can use that newer formula we're doing. So they're both kind of gross. I'm just going to use that newer formula if you don't mind, even though I really don't like it. So the first 10 years of work. Let's see here. His first year we just found to be $33,700. And then up in the numerator, we have a 1 minus, make sure you use parentheses here, 1.045. Did it again. All right, and then we're putting a 10 up there, remember, 10 years. And then down in the denominator, another set of parentheses for 1 minus 1.045. Don't need a parenthesis around that R this time, but you do need it around the denominator. Face, get out of the way. All right, when you type that in, now you're really dying for an answer. I don't even have it. Oh, man. Okay, I got an answer. Moment of truth, y'all. 4, 1, 4, 1, 1, 2. 0.66 cents. What is that? I guess that kind of makes sense. You know, if you just divide it by 10 years, it's like 40 something. Man, this is a case where I really needed students with me because I think I messed up like no fewer than 7 times during that video. I apologize. Thanks for hanging with me, watching that whole horrible video. Ask any questions you need to ask through email. And good luck. Bye.